things. I have to slightly correct you. I'm working for Hewlett Packard Enterprise. Hewlett Packard doesn't exist anymore. Since 5 years, we have split into two new companies. One old company, but they also changed their name, and I'm working for Hewlett Packard Enterprise. And I'm not going to talk too much about that, but just in general, what are we doing? We're selling big hardware equipment to, universities, hospitals, enterprises, and so on and so on. But yeah, this seminar is going to be more research-minded than talking about what we sell. And I'm immediately going to dive into this. So the topic of today is going to be how we are researching to make hardware to solve NP-hard problems. And I think most of you guys have actually a very strong background in this. So the slide deck that I have is kind of the thing that I normally give to people with a more physics and engineering background. I did try to add a little bit more mathematics. But yeah, we'll see how it goes. You can definitely feel free to interrupt me when I'm going too slow or too fast somewhere. But yeah.
Can I interrupt you? You should call it NP hardware.
NP, indeed. That's something that we haven't thought about yet, but I'll give it to the marketing team. They will definitely appreciate it. So the thing is, like, yeah, what is an example of an NP-hard problem? You have the traveling salesperson who wants to visit a couple of cities and wants to optimize the optimal order to do this. And as some of you already might know, is that if you have, say, 5 cities, then there's 12 possible ways of doing it. If you have 15 cities, you get 43 billion possible ways of doing it. So it's impossible to write those things down. You really, you need an algorithm to do this. And then there are ways to exactly solve this, but that also gets way too compute intensive if you look at the scales where those problems typically appear. So people then are starting to use heuristics. I think on the right of the slide, you see a list of use cases where people think it might be relevant, like airline scheduling and so on. This is actually also something that we as a team have less experience with. So if that actually is something that you know a lot about, then you can also contact me during or after the presentation, but I'll get back to that at some points. So yeah, that's the idea. What are people doing on the hardware side? In contrast to AI, where there's actually a lot of companies trying to make hardware to speed up calculations for that application, there's not too much going on for like from the business perspective or from the company perspective of companies that try to make hardware for optimization problems. There's one exception in the center, and that's what you see at the bottom of the slide. There's D-Wave. For a decade already, I think they've been trying to make quantum annealers, and they claim that that would actually help to solve combinatorial optimization problems. But there are some disadvantages, like you have to cryogenically cool those superconducting qubits. It doesn't scale very well. It's also very expensive, and at this point, this technology is not yet that mature. So what do people do at this point? At least from our own research, we notice that they use traditional digital hardware and they use software tools like Garobi, and then they try to solve problems. And like one of those problems could be the NFL scheduling thing, where you have like 256 games that you want to schedule. That's not too much, but then if you map that to like a mathematical version of that problem, then you already get up to 20,000 variables. And apparently, if they want to solve this, then this whole process of assembling that schedule, which actually seems as a simple problem, but apparently is very computationally intensive, takes you 3 months on a 1,000-core system. So that's good for Hewlett Packard Enterprise because we do sell those systems, but it's not really good for the customer because they obviously would like to do this more efficiently. And so that's where we see the opportunity. And so what happened recently, some researchers noticed they came up with another type of hardware, an optical system, and I'm going to explain that later in more detail. And they call this a coherent Ising machine. So that's the CIM that you see on the slide. And they compared this system on a particular benchmark task to D-Wave. And then they noticed if you check the problem size, that's the x-axis, and if you check the success probability, like it's an heuristic, it's a probabilistic way of running things on this hardware. And if you just run it once, then you only have a probability to reach the optimal solution. And so that's what they track here. And you can see that the probability for the colored lines, which is the D-Wave system, the quantum system, is way lower than the black system, which is the optical system. It has a better scaling. And then you can convert this probability for a single run into the total time that you would need to run the problem to hit the optimal solution with 99 success probability. And then you get obviously like extremely bad scaling for D-Wave as well. And so this is kind of the incentive that we also had to, yeah, okay, apparently there's a classical optical hardware system that actually is able to outperform optimization problems, at least for this type of benchmark task. So can we implement this? And so I'm going to do a little bit of a deep dive in the comparison between the two systems. First off, what are we trying to do? We're trying to minimize a Hamiltonian, and that looks like this one here. And so you see spins, which can be +1 or -1, they're coupled. Those are quadratic terms. You have those coupling terms, and those can be programmed. And then there are two different ways of like going through your energy landscape. On the left, you see the quantum annealing approach, where people claim that like, hey, if you have quantum mechanics helping you, you can tunnel through error barriers or energy landscape barriers. And that can help you to avoid local minima. And with the other system, and I also will get back to that in more detail later, they claim you have your energy landscape, and then we come up with some kind of a gain mechanism that is represented by this red line, and we increase the gain slowly, 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 until this gain line is going to hit the global minima of this energy landscape. And at the moment that you do this, then apparently your system is going to start oscillating or being present in the optimal state that you care about. So it's hand-wavy explanation, but that's in a nutshell how people see this. And both systems can actually be seen as some kind of, like a recurrent neural network. And that's what you see here. You have a matrix vector multiplication unit, you have a feedback loop, and then you have an array of binary neurons. And those binary neurons, there's different flavors of having this nonlinearity here, but this like updates then over and over again the inputs of the matrix vector multiplication unit. Depends, like some versions of this hardware are going to be continuous time, other ones can be discrete time. Only in the discrete time, it's like a really clear way of seeing this update equation. And so how did the optical team do this? They came up with something that at first sight looks completely different, but the key mechanisms can also be discovered. You see this loop here. This is an optical fiber. It's in a loop, so that's a recurrent feedback loop. Then you see this FPGA. This FPGA is just digital hardware that can do matrix vector multiplication, and it taps off a bit of light, measures it, then does the matrix vector multiplication, modulates some light, and sends that light back. And then there's this thing. This thing here is a nonlinear unit that actually is going to represent those neurons that I was talking about before. And in physics terms, that's called a phase-sensitive amplifier. I'm not going to talk too much about those details here, but in principle, the only thing you need to remember is that this thing is pumped, and we can increase the strength of the pump with pulses. And at every pulse, you actually have a chance that you can be in two stable states. So there's going to be some symmetry breaking, and the phase of the light is going to tell you in which state you are. So that's representing my binary neurons that I was talking about before. And the thing, why do we work with pulses? It's because we only have one nonlinear unit in this case, and every time a pulse hits the system, it represents a new neuron of my Hopfield or of my Hamiltonian that I was trying to implement. And so with this thing is also not only doing the matrix vector multiplication, but it's also internally, you can see it as a delay line that is actually making sure that you can couple
Thomas,
yeah,
there
go
is
ahead.
someone who has raised their hand. I think they have a question.
Mm-hmm.
Do you want to answer it now?
Sure, yeah.
Sorry, do you mind if I ask the question now?
Yeah, no, go ahead.
How sensitive is this FPGA to losses in the optic circuit? Like,
Wait, I
what type
didn't
of
understand.
noise affects the FPGA? Like, the FPGA is basically at the core of the circuit, right? If your FPGA screws in a matrix multiplication, then your whole loop, doesn't work properly. How sensitive is that to the pulses and
So
whatever you
the
put
thing
in.
is actually this FPGA is digital hardware, so in a sense it's very robust against noise. But I think you might try to, or like your question might be related to the fact that if you, for instance, if you would want to do this in the quantum regime, then because you measure your quantum states, you actually lose some of it there. And so there are also ways of researchers who have looked into whether they can do this all optically. Actually, I will get back to that later on. And then the other thing is you're talking about noise that can be bad. Maybe hold that question for now, because you'll see I'll get back to that point a couple of times. So I don't fully understand the question at this point yet, but maybe I'll answer it later on in the presentation by talking about some other bullet points. So
Okay.
just, and if I don't, then obviously ask me at the end.
Thanks.
Can I ask a question? So in this left corner circuit, so you measure the light somehow, and then out of that comes a vector that you put into this matrix multiplication.
Yeah, exactly.
And then
the vector is
generate
here.
some light that goes back into the loop somehow.
Yeah, indeed. That's the accurate representation of what this thing is trying to tell you. And this is only one way of doing things. You'll see actually that I'm in a second, I'm going to talk about other ways that try to do the same thing, but then not with pulses. You can do it continuous time. Sometimes it's discrete time and so on. But this is where it all started. So that's why I actually wanted to highlight this system.
And then how is this vector represented in light? Are you going to say something about that?
Yes, that's actually a good question. So in this case, they do, and this is, yeah, if you have a physics background, you might be able to recognize this thing here. Here they do a homodyne measurement, and they really try to represent, like light is a complex, can be represented by a complex variable. That's a little bit overkill for what we normally need in the Hopfield and the Hamiltonian there. But we can measure it, and actually in this case I think for the FPGA they only use one of the quadratures of that complex variable. So that's actually what I was saying before when I was saying this is a phase sensitive amplifier. There's amplification around one particular phase, and it's that thing that you want to measure, and the amplitude there is what you put into the FPGA. And later on, I will talk about a system which is electronics based, where you only have real valued variables. And then I also will talk about a complex valued system, which again, and I'm not going to dive into too much details there, but actually is based also on a phase sensitive amplifier, but implemented in a different way. So it's when we talk about lights, it's complex valued. When we talk about electronics, you're only going to have real valued amplitudes.
But what is the dimension of this vector?
The dimension of the vector is going to be the number of nodes that you want to implement, which actually is going to depend on the problem size.
But I mean, in the light version, do you have like different frequencies, or?
No. Okay, good question. In this case, actually, we do have different frequencies living in the setup, but in the thing that you care about computationally, there's only light at one frequency going around and around. That's actually very important, because that means that we can use coherence, and coherence means that like light can interfere, have destructive and constructive interference, and that's important to make this phase sensitive amplifier work. So all the light is encoded on the same wavelength. The information you care about is going to be the amplitudes following a certain phase that you can pick this. And the phase is actually with respect to some pump lights that this pump that we use is going to give you a certain phase reference. And then you have this symmetry breaking. So you have either 0 or pi phase with respect to that pump. And that the amplitude in those two quadratures is going to be how you represent your light.
And so so like the entries of the vector are encoded in sort of in time in this?
In this case, yes.
Okay.
Yeah, actually, as you can see here, those pulses here, this would be, for instance, like a 4-node Hamiltonian that you want to implement, and you see some feedback coming from the FPGA.
Good, thank you.
Welcome. So yeah, this is a little bit of visuals about how things are for a quantum annealer, and in the interest of time, I'm going to skip over, but the conclusion is actually that if you check a couple of numbers of those two systems, like the number of nodes, how much power it takes, and whatever, the Ising machine they claim that they can also operate this in the quantum regime, but we actually think that that's not really necessary to make it work. But the key thing here is, why is this system so much better than the other one? It's because we can have all-to-all connectivity using that FPGA. Whereas if you are implementing things using a quantum annealer, you are working with superconducting qubits in this case, which is actually, it's very difficult to make those qubits couple with a lot of other qubits, because then you destroy their quantumness. And just having that limitation is actually making that it's scaling so badly, as I showed in the figure before. And yeah, some other numbers is also, this is actually already pretty expensive. This Ising machine, it's a tabletop setup, it looks like this. Whereas D-Wave, like, yeah, you need to pay $15 million to be able to work with one of those systems. So this is a factor 15x, but actually, yeah, I'm going to talk about systems which should, again, be way cheaper than this number here. Okay, so how do we do things in HPE? I already mentioned, go ahead.
Question.
Sure.
So on the previous slide, you crossed out the quantum.
Yes.
Why did you do that? Because you also crossed it out with D-Wave. Now, I'm not a big fan of D-Wave, but
yeah, the flow where I normally use this slide is actually to say, do you really need quantum? And then my thing is, I would normally say that both systems can actually have access to quantumness. D-Wave definitely, they do have access to quantum states, but the key question is, do you need it for applications that we believe are relevant? And that's something where we are not really convinced yet that the combinatorial optimization problems that people care about, that you would have that quantum effect there. And so that's why I crossed out that. But that's something which is up for debate, obviously. I think the people from D-Wave might have different opinions. Okay, so the two systems, you see two chips here. The left one is an electronic version, and then the right one is a photonic version. My background is photonics, but since a couple of years, I've also worked with the electronic team in labs. And I think I'll start with that one first. And yeah, as I already mentioned, both systems are purely classical in our case. So how do we do this? In labs, we've had some research before where we were trying to speed up matrix vector multiplications, because that's actually a very computationally intensive task. And as you remember from the figure that I just showed you, like with the Ising machine, we wouldn't have to do we would have to insert an FPGA there, so digital electronics to do this, which is cumbersome. So that's why we care about it. And so my colleagues were looking into, can we use analog computing to execute matrix vector multiplications more efficiently than what you can do in the digital domain? And they noticed that, yes, there's a way to do this, and I'll explain how. But take home message is that it can be definitely faster, like 10 to 100 times faster than compared to GPUs. So that's like another way of doing this in the digital domain. It's also faster than the most advanced digital accelerators for this, like say Google's TPU, Tensor Product Unit, and so on. And the key reason is because we use some properties of physics that allow us to represent information in a more efficient way, and that actually makes it both faster and more energy efficient. And the thing is as well that that team already has worked on the whole software stack to be able to map your AI problem or whatever you care about onto a compiler, and that compiler can then map it to instructions that can be understood by this hardware. And so what is the key ingredient that we use? It's called a crossbar array. So you see a couple of voltages coming in here. Those are my inputs. And in this case, I'm going to have output currents. They come out here. Actually, no, they come out here, but you can again convert them back to voltages. And then we are using Kirchhoff's law and like just some basic electronic laws of how things are doing. And you can see that you get a matrix vector multiplication here. And how is this matrix vector multiplication organized? Like at every intersection between those lines in both directions, you see this element here, and this is a resistor, but it's a special one. It's a tunable resistor. So we can program its state in there. And by doing that, you can actually implement more than one bit in a single device. And because we can do that, and also because those resistors can actually be you can make them very tiny, which has some energy efficiency advantages, this thing becomes, you get those numbers that I just mentioned, here. So that's how you get to those numbers. So just remember your resistors from high school physics, organize them in a crossbar array, And then using some advanced processing, you're able to come up with this matrix vector multiplication. And just doing that really has an impact. And so the question is, we did that before, can we reuse it for my combinatorial optimization problems?
Can I ask a question here again? Because what is actually the complexity of this?
In this case, this is just like polynomial, right? I mean, this is
sure, but as you probably know, there's sort of a big open question in complexity theory to figure out, theoretically at least, what is the best algorithm for matrix vector matrix multiplication. Oh, this is only vector matrix multiplication that you're doing here, not matrix.
This is, you can actually, yeah, this is vector matrix multiplication, and then I do think it's also possible. No, wait, no. On the current prototypes that we have, we only do a vector matrix multiplication, but then there's like the software tool around it to also do the more general case. But in principle, this is actually just doing a single step. Like time complexity wise, you have the whole vector available there, and at the same time you get that output there with some delay, which is determined by the physics. And so the thing is that, like, yeah, in some cases, for for dense matrix, I think that's the best you can do. But then for maybe for some sparse matrices, if you use clever algorithms, you might get better complexity than this thing. But the key thing to think about here is that we actually are going to implement very basic units. And one of the key questions as well is going to be like, now we know that we have those units and they become way more efficient than what we have done on digital hardware. Can we rethink or profile our hardware or algorithms that we had before? And can we get some speed up because of that? And so for sure, in classical AI problems, those advantages that are there. You can really calculate the energy that it would take to run this on digital hardware versus what you do here, calculate the speed, and we get those numbers there. I don't really know the scaling there, but it's definitely, yeah, for the end user, the difference is really there.
But this somehow looks like a parallel algorithm for matrix vector multiplication.
Exactly, this is definitely parallel.
The time it takes.
Can I? Sorry, there's a very old idea in digital hardware called systolic arrays, and this looks a lot like this. Have you looked into that?
So yes and no. In fact, some of the digital accelerators that are using this, they're indeed using systolic arrays, and that's how they got their efficiency. And then the thing is that just in the hardware unit itself, we don't really do this. But then if you're going to, because at some point this crossbar array is going to have a finite size because of hardware limitations, and then you need to have a couple of them to map a very big matrix to it. And at that point, we're starting to implement those ideas that you're talking about, because we really want to make sure that the data is also flowing optimally on the chip, that nothing is waiting for another calculation that is living super far, maybe on another chip, and because then you also have a communication overhead.
Okay, thank you, and sorry for interrupting the previous question.
No worries.
Sorry, I also have a question. May I ask now?
Sure, yeah.
So these voltages, they represent real numbers?
Yeah, real values. But obviously there's going to be some noise. So there's a finite accuracy. And in practice, we still talk about, like, for a certain voltage, how much bit resolution that you have. It could be like 4 bits, 2 bits. Depends on the choice you make.
There's no error correction for analog computation.
That's a very good question. And in principle, I'm not going to talk about it, but there are people looking into that now, because obviously there's an advantage to try to do some error correction there.
But I think von Neumann once showed that it isn't possible.
Yeah, but okay.
In
so
very early days.
So that's a thing that I have less background there, and so I'm not familiar with that proof. But I can tell you that by implementing a bit more overheads, you are able to, still to improve the outcome of your result, or at least detect that you have errors.
No, but it's okay to do just noisy computation. There in your, I don't know, output function, there will be some noise maybe, but if it's low enough, then.
Yeah, this is actually, so the remark there is, this depends on the application. In some applications, you really want to get rid of the noise, and then the thing that you decide is, how many bits can my hardware deal with, and then you live with that, and then normally the outcome should be kind of noiseless
Mm-hmm.
in practice.
Yeah, it's kind of comparable, I think, to the noisy quantum computers we have the coming decade that can still be useful. So.
Exactly. That's also, yeah, there's a little bit analogy in that sense that like we are not using quantumness, but we try to see just by using analog computing, are there other things that we can do that are less easy to do with digital computing or more efficient? And there are some trade-offs to be made for sure. It's not a holy grail, but apparently we can get some benefits. Okay, I'm going to continue. I'm a bit behind schedule, but okay, and apparently there's also something wrong with my slide here. Yeah, again, this is the thing that I was showing before. What is this thing doing? What we actually are implementing here is called the Hopfield neural network with memristor crossbar array. And this thing is doing a gradient descent algorithm. This is the matrix vector multiplication. This is the binary we put a comparator there. And then like, yeah, you compare the outputs of the matrix vector multiplication compared to a threshold, and then you determine your state. If you do nothing special, then you will get stuck in a local minima because, yeah, that's how Hopfield neural networks work. The methodology there is that typically you determine your problem that you want to solve, which type of flavor it is. You map it to a matrix. You determine your initial state vector, and then you iterate over and over again. And I think that's probably pretty easy to understand. So what you then do is you map the matrix that we had to a matrix of those crossbar arrays, as I already explained before. And then this is how it looks like. And I'm going to move this thing here. So yeah, normally you get stuck in local minima if you just have a noiseless Hopfield neural network. If you do add noise, you're able to jump out. That's our quantum tunneling, but it's actually, you can also see it as simulated annealing, or that's at least what we do. Hardware can have noise, and so normally we were talking about where you want to suppress it if you want to have a certain outcome, but some algorithms that we have also in digital hardware require random number generators to generate noise. Yeah, to get good performance. And that's the same thing with this Hopfield neural network. Actually, you want to have noise. And then you see the energy here is decreasing as a function of time. If you have no noise, you get stuck very soon in local minimas. If you have too much noise, yeah, you don't get to the global minima that you care about. And if you taper it or you have an optimal level of noise, you can actually get to the minima that you want to have. So there's an additional term here that gives you a little bit of variability. And the good thing about working in the analog domain is that actually it's hard to suppress your noise. So if you can use it as a computational primitive, it actually gives you an advantage. So that's the key idea, and I'm going to talk a bit more about it because there's different ways of generating noise. And this is actually going back to the question that we just, the thing that we were just discussing. If you implement weights with this matrix vector multiplication and you set a probability histogram here and you measure the errors here, you get this type of curves. There's actually other ones, sometimes they look more Gaussian than this one, but just as a reference, we do have indeed implementation errors. Those errors, they scale with the array size. So if you go to bigger array size, then yeah, you get more errors. This is the standard deviation of the noise. And this color code that I have here, this orange here, is actually saying that your error is going to be bigger, too big to be able to have finite precision for a certain task. So if you are below here, you're guaranteed that yeah, you will still have an approximation because you work with analog physics, but it's your result. If you then discretize it, would still be fine. If you go above here, then actually your discretization is going to give you errors, and it depends on the density of your array size. So there's two different colors here. Okay, so that's again something similar, but then yeah, if we solve that Hopfield neural network, we run it for some cycles, we check the probability to reach the optimal solution, then you can also go back to what is the type of noise level that we need. And you see with the decaying noise level simulated annealing, you get actually pretty good probabilities here. Fixed noise, you also do better than having no noise. In a sense, key take-home message here is having fixed noise gives worse performance than tapered noise, but definitely it's still better than no noise. So my errors that I got here, they're fixed, like they will not change as a function of time. So then the question is, how can we control this? And that's something that we do with something that we call a Schmidt trigger. It's an idea from analog electronics as well. And the key idea here is just that you have some kind of hysteresis. So we are going to have an hysteretic threshold. And so normally they also use this in analog electronics to clean up signals. Like if this is your input signal, If you just have this as a threshold and you flip every time this signal is flipping over the threshold, then you get like a very noisy signal in a sense. But if you have hysteresis and you only flip if you go over this barrier here, or if you go over this barrier there, you get a way cleaner signal. And this is a thing that we can control because we can control the width of this hysteretic loop here. So this loop, if we control this, the width here, then by doing that and combining this with the intrinsic hardware errors that we have in our matrix, we also can do something which resembles simulated annealing. And that is something that I show here. This new black line here is getting very close to the decay noise level of the simulated annealing. And that's actually showing that we can use intrinsic hardware errors that we normally want to suppress in a good way to represent classical software algorithms such as simulated annealing, but then way more efficient. Okay, I think I already explained that before. And so, okay, more measurement results, or like now some measurement results. This is like similar curves as what I showed before, no noise, tapered noise, noise that is not controlled. And you can see that the tapered noise is actually doing a pretty good job. Once you do that, you can also calculate success probability as a function of the problem size. By doing that, you can again calculate the time to solution. So how many times do you need to rerun it to solve a problem with 99 success probability? And you can also calculate how much energy it takes, again, as a function of problem size. And what we then did, and those numbers are actually like based on our experimental results, but it's done in simulations. And then we put everything in a table and we compared like one data point for a certain benchmark task with other systems like digital computing, that's what you see here, optical computing, that's what we see here. This was our starting point. And then you also see quantum annealing. And then we come up with some metrics. And in a sense, if we talk about energy efficiency, then we can really see that we outperform digital computing with a factor 10,000. Now, disclaimer here is that digital computing, the systems that we compare with here are way more general, more scalable at this point. And at this point, we only compare with a tiny core with a memristor crossbar array. We don't have the full architecture around it yet. So we would need to do a full architecture design that's going to give us a bit of trade-offs, and we will lose some of this benefit. But the thing is, if this was only going to be a 10x improvement, then there would have been no room to even think about making an architecture. But we start with this big benefit, and so thinking about the architecture makes sense. We think we still should have some benefit if we have the full architecture around it. So that is one system. Then I'm going to talk about the optical system. It's again the same format. You have binary nodes, or nodes that are supposed to be binary, then a matrix vector multiplication. Two things you need. One thing is the matrix vector multiplication that we now want to do using light. What we use there is coherence. I talked a little bit about it during question before. So in basic physics, high school physics tells you if you have two waves, and the peaks and the dips of those waves align with each other, then you get a stronger wave. If they are not aligning with each other, then they cancel each other out. And just doing that allows you to, in a controlled way, allows you to route light in any direction that you want. And by doing that, we can actually use something that we call a Mach-Zehnder interferometer. That is this component that has two inputs, two outputs, is just doing interference. And you can see this as a unitary 2x2 matrix multiplication. So this thing here. And then we put heaters on little rods of light on the chip that can control this, and then you can really control every variable of this unitary matrix. Once you do that, once you order them in like this type of triangular array here, those triangles here, then you can actually make a general n by n unitary matrix. So if you then have a general matrix that you want to represent in your hardware, what you do is you do an SVD decomposition, singular value decomposition. And yeah, you have two unitary matrices that you build with those basic building blocks. And then you have a diagonal that is also very easy to implement with this type of building block. And then you can make this thing happen on your chip. And there are already some experimental results. That's what you see here. So this is one group that has done this. I don't know, one group has done this for two different applications. One is for quantum transport simulation, and they use the same chip for optical neural network simulations. But in this case, they only executed the matrix vector multiplication on the optical chip. Again, this is using single wavelength light. Amplitude is represented in the, or like information is represented in the amplitude of the light. And in this case, I'm not working with pulses, but this is just parallel computing, very similar to what we do with the Hopfield neural networks. So we have all the whole vector at a single time instance at the input, and almost instantaneously you also get it at the output, because this is just time of flight of light. And this idea was pretty successful, and now there's like 2 startup companies that actually are looking into commercializing this for AI applications. And I think recently they even made a prototype with that could do a 64 by 64 matrix vector multiplication. So that's pretty good, but we're still waiting for the academic paper to talk about the bit resolution and things like that. So that's key ingredient 1. Key ingredient 2 is my Ising nodes. For that, I'm using cavities, so ring resonators in this case. What you can imagine is that you will have little rods of light, waveguides on a chip, this thing here, and then you have a little ring next to it, and some light is going to leak into the ring and then make round trips there. And then the wavelength of the light, how many times, integer times that fits into the round trip length of the ring, is going to determine whether it will resonate, stay in there or not. Like similarly to your snares or instruments, there as well, wavelengths or the frequencies, they really have like an integer relationship with the length of those snares. Same thing with this light here. And then the thing, or the fun thing to do is, okay, so if you get closer to the wavelength of light or the resonance frequency of the ring resonator, you'll get more buildup of energy inside this resonator. And then you can come up with your light. This is representing my laser that is getting close. And then at some point, if there's a lot of light in the ring, it can actually change the properties of that ring. So it's going to change maybe effectively the length of that ring, and so change the resonance frequency. And so that's what you see here. Like if I have low power, my resonance frequency is here. If I have high power, it's kind of here. And by doing that, and I just wrote down the rate equation there for this system. So it's something basic like complex variables A, you have detuning, lifetime, light coupling in. That's how we can represent this. And then what you can do then, because you have this nonlinearity, if you, again, keep your frequency fixed, you ramp up the amplitude, you can check the output and you get this S-shaped behavior that's just due to the nonlinearity. You can even get bistability if you want, but we are not yet that close. We're slightly bistable, but the main thing that you can do is you can interpret this figure as like having 2 states. You have one state that would represent with your +1 state of our Ising nodes, and one state would be represented by my -1 value of my Ising node. And the thing there is that, yeah, you can see that those states are asymmetric because of the physics of the system. But in the next slide, I'll show you that there's a way around that, and you can make it a more symmetric system. Then we organize all those those cavity-based, ring resonator-based nodes here. So we have an array of nodes. In this case, we have 4 of those. Then we have those multi-path interferometers based on those MZIs that I've talked about before. More difficult to see is this feedback loop that you see there. And then you see some control units that can really program this whole thing. And so this is something that we implemented, but unfortunately it didn't work yet because the technology wasn't mature yet, but we're still trying to make it happen and really make a chip that has all optical Ising machines integrated on a chip. There's also some other groups that are studying this. Okay, and so a little bit more details about my Ising node. Instead of having 1 ring resonator, actually we think it's better to work with 2 because you do that, like normally every ring resonator has 2 states. So because we have 2 rings, we would have 4 states, but then we add a feedback loop and we make 2 of those 4 states unstable. So we have remaining 2 other states, and that gives us a symmetric system that actually has the nonlinearities that we need. And yeah, this is how it looks like on a chip. But then a bit more equations. So those are the rate equations that represent my system. You can do a Taylor expansion and you get a system like this. If you have, based on your background in nonlinear dynamics, you would be able to recognize this 3rd order term, this linear term here, and you can see that it's indeed dependent on what happens here, and this is dependent on the pump power. You'll have a pitch fork bifurcation. So you ramp up your pump. First, there's like no light coming out of my state there. At some point, the no light state becomes unstable, and then you have states like 2 states, and they only differ in phase. The amplitude is kind of the same. And those 2 states is what represents our information. And so that's what we see here. we ramp up the pump, so that's the signal here, then we keep it fixed. So at first we only have noise in the system, and at some point it starts to bifurcate. And this is like a lot of time traces of like, I forgot what it was, maybe 100 nodes, Ising node systems. And then you see like the histograms on the amplitudes of those Ising node systems in each state. And this is the energy of a couple of runs during such an annealing thing as a function of time. And you see indeed that the energy for the problem that we were studying is going down. And then you can also get some like statistics on that. So that's how this works. So in this case, it's continuous time rate equations that you need, whereas for the electronic system, we were just using discrete time things. And yeah, I think I already explained most of it. I just want to mention that why are we doing this actually? It's because photonics might have the advantage that we could be a bit faster than what you can do with electronics. That's one thing. And if that's true, if we are indeed able to do it at very high speeds, then we should also be a little bit more energy efficient as what we can do with the analog electronic system. But the disadvantage of this whole thing is that this technology is at this point less mature. And also because of the wavelength of light, it has a way bigger footprint than what you would be able to do with electronics. So we think it might be useful technology. That's why we're studying it, but it also is going to be probably mainly relevant for applications where you really care about latency, because that's a good thing of this technology, and where you really care about maybe processing information which is already in the optical domain to start with. So yeah, that's that. I'm trying to go to the next slide. So what's next? The things that I've talked about before, that's actually what I normally share with people when I'm talking about this research. The next couple of slides is more about something where we don't really have the expertise, but to give you a little bit of context of where, from our hardware team's perspective, where we think there's actually some challenges and where we hope that maybe the research community can also help us. So first off, there's this question about applications. What do we do there? One thing is, I'm just going to talk about one example, not really in detail, but just to give you an idea of what are the things that we're struggling with. If you think about the knapsack problem, and one of my colleagues did just like some Googling around, and he found like a lot of variants of this thing. So he found all those ways of implementing knapsack problems, or and then, yeah, there's so many options that we actually don't really know. If we want to show that our hardware is relevant for something that people care about, which of those variants would we have to implement? That's like one of the things that we have a little bit of an issue with. Another issue is that even if you just stick to one of those problems, then you Google some papers, and there's some very old work on it, some more recent work. But in a sense, there are actually also different ways of mapping that knapsack problem to the Hamiltonian. There are algorithms, but then even within one of those choices, you also have some coefficients that you need to tune, because in a sense, the hardware that we have is able to solve quadratic unconstrained binary optimization problems. But in a lot of the problems that we face with, we have constraints. So then you need to add those constraints to your Hamiltonian. That gives you some kind of a choice in 3 parameters where you force that penalty terms that you have to add, those penalty terms that you need to add. And so how do you optimize those? So that there's like some questions there as well. Other questions that we have is then, if you look into that field and all the papers that are out there, then in some cases, for some applications, we're lucky and we see that like people run this thing on hardware for their benchmark task, and we can get some numbers and we can compare ourselves with that. But it's not always for the same task. So that's a little bit difficult for us to keep track of how we convince people that we're doing something relevant. And also for every other field, we might have other benchmark tasks as well. So that's not really, yeah, like we are a small research team, so we really need to focus, and it's difficult to know what we then have to focus on. But still, like, we did some back of the envelope calculations. This is again time to solution. So how long would it take to get a very good solution? Only the purple lines here are the ones that we care about. This is something that we took from literature and we rescaled it a bit to newer hardwares. This is what you get on a digital hardware thing. And then this is something that you get in analog computing on our system, and we see that we get a benefit. But still, we're not really convinced that this is what we need to do, because yeah, maybe this wasn't really the problem that we wanted to compare with, and so on. So finding applications that are useful, mapping it to our hardware, that's something that we still struggle with. Then the other thing that we struggle with is algorithms. I think I already showed you a couple, or like tried to explain a couple of different algorithms that are physics inspired. Like you have simulated annealing, you have quantum annealing. You have actually, if you look at D-Wave, they use adiabatic quantum annealing, where they change the energy landscape from a system where it's easy to get the ground state to the problem that they care about. And then you have the Ising machine, where you have this gain function that is going up to a loss function that you're able to program, and that things start to oscillate in the global minimal solution optimally. Yeah, question there is for D-Wave and quantum annealing. Quantum annealing, for the quantum tunneling, you really need to have quantum effects, I think, to make that happen. We bypass it by using simulated annealing. Then this adiabatic thing, that's something that we actually thought that we could implement. And that's, yeah, we have again some energy landscapes. So most of them I already explained, but I want to just say that we have looked into doing classical adiabatic annealing, or having our flavor of it, because we think that might have some benefits. We're also looking into relaxation techniques, where we come up with an initial guess that should be closer to the optimal solution, and then throw it to our hardware. And we're also looking into, and that's only very new work, but we're also looking into more global optimization routines like Bayesian hopping, where we switch local search techniques with also things that then will scramble your solution vector and bring you to other basins of attraction of other local minima, and hopefully that gives you then eventually the global minima that you care about. Other things we've thought about is like parallel tempering, things like that. So a lot of heuristics. We are now trying to look into whether we can map it to our hardware. And I'm seeing that 10 minutes left, but I think I can. I just wanted to show that, like, for Bayesian hopping, or no, I mean classical adiabatic annealing, right here you can see an experimental result. And I can also say that if we compare quantum inspired or classical annealing solutions, then we indeed get a benefit compared to directly solving things. And we get similar things for using relaxation and also Bayesian hopping. So higher success probability in this case as a function of problem size is better. So simulations prove us that using more sophisticated algorithms on our hardware makes a difference. But then the question is, instead of like just working with pre-existing algorithms, given the constraints of our hardware, can we redevelop algorithms and do things with that? So that's another thing that we're starting to think about.
Can I ask a question?
Yeah, sure.
So you talked about the constraints of your hardware, but I'm not sure. I had the feeling you discussed multiple setups, maybe not. But what? So because you mentioned at some point that you can do matrix multiplication, matrix vector multiplication, which seems quite general. But then you also discussed these Hopfield neural networks. So what specifically can you? What are the sort of the basic building blocks that you can do with your hardware? It's not entirely clear.
Yeah, so the basic building blocks with all flavors of the hardware that I talked about, both the optical one and both the electronic one, is this matrix vector multiplication unit. That's where it all starts. In some cases, in both platforms, we're also able to implement nonlinearities. Either it's going to be just a comparator, so a threshold. And in other cases, we can actually have a tunable nonlinearity, like we can have a sigmoid, tangent hyperbolic, where we can change the slope at 0. So that's another thing. And then other things we can do is just implementing feedback loops. So that's the key thing that we really want to implement on a core. Then on top of it, in practice, because we know that the problems that we want to solve are going to be bigger than what we can have in such a simple core, we also need to think about how are we going to link those cores together and have some kind of a hierarchical hardware. So those are things we can do, but then there are some things that we can't do. Like for some algorithms that you want to implement, you might need to calculate, for instance, an exponential or another function. And so when you work with electronics, you might put some digital logic close to your analog hardware, and then you can do this. When you work with photonics, implementing that might actually be super difficult. Maybe you again need an FPGA or another digital electronic compute unit there. And so what we're trying to look for is algorithms that are simple to map to physical components on our chip. And I listed some of those components, but it depends a little bit on the algorithm for us to know which type of components that we are trying to implement. So it's like it goes back and forth. In principle, you want to optimize both your algorithm and your hardware at the same time, I think.
Okay, thanks. And I had another question. You mentioned that quantum appears in what you're doing, but it wasn't. How does it?
Yeah, that does it. I actually didn't. I did mention that it's there in the research team that was trying to do this with a fiber-based setup. That's the optical system that I was shown initially. They claim that they have quantum states in their system, but it's kind of a debate whether that's, and the reason is because they go to, they use squeezing effects there. That's because they have this phase sensitive amplifier, and I'm not really an expert there, but it seems indeed that they can prove themselves that they are in a quantum regime. What they haven't really proven yet is that that quantum regime really helps in giving you computational benefits. And so in simulations, they come up with quantum descriptions of that system, and they show that in that regime it definitely works. But is it really necessary in the experimental setups? I don't really know. What I do know for sure is that the experimental systems that I showed, the work that Labs is doing, that we don't have this. So there are no quantum effects there because we are not optimizing our system for that. It's way too lossy at this point. With electronics, there's just no way that we would get it. With photonics, we would be able to get it, but in my mind, that's something that maybe I will be able to reach to maybe in 5 or 10 years, dependent on the funding that we get. And we really need to reduce the losses there. So it's actually, I was going to go back to that later on in this presentation when I was talking about open research questions. I see that I have 4 minutes left, but I think I can kind of summarize. I already talked a little bit about, problems typically have way more variables than the hardware that we do. So what do we need to do is something that I visualized here. We need to have a couple of cores, link them together. Big question is, how do we do this? Because we might actually lose some of the benefits of doing this in the analog domain. Then conclusion, I talked about two systems, an electronic one, an optical one. Both of them are definitely better than digital electronics for the small benchmark task that we talked about. They're also doing better than quantum annealing at this point because quantum annealing doesn't have the ability to have all-to-all coupling between the nodes. But then the thing is, like, we need to develop a new architecture around it. That's one thing. And the other thing is we really want to solve problems that people care about. And typically those problems are a bit more dirty. So they give you maybe not only binary variables, also continuous variables. Maybe they don't give you just quadratic terms. They also give you higher order terms. So there's a lot of questions from our side to see how we can take state-of-the-art algorithms and implement our hardware in there and then see whether there's still a benefit. That's what I was talking about before. Yeah, I'd already mentioned that's also studying our setup, the photonic system and the low photon limit would actually be interesting. And then I have, and this is what I'm going to end. This is just a couple of questions that I'm asking myself. I'm not going to read them out loud, but yeah, you can just go through them while we maybe discuss some other questions that we have, that you guys have.